We're going to talk more. You need one of these too? More about polynomial functions. Hopefully tomorrow we'll actually start graphing these, but today we're just going to talk about more things that we should know to graph them. So I put these lovely graphs on there. I should have been prepared and actually graphed them for you on here so you can see them better. But I want you to see what happens when you, if you graph x squared and x to the fourth. Hello, why isn't this working? It's thinking about it. It's thinking. And then why didn't I put day 2 up there? That's. What do they count? Oh, they count. How long it's almost 100 days of school. If we don't miss any school, Thursday is the 100th day of school. Just in case you're all wondering. That means we have 80 more. Yes, Parker had to bring 2 boxes of Capri Suns, so I put them in his backpack today, and let me tell you, you would think he was carrying a ton of bricks in there, because he just kept falling over, he just kept falling backwards. They have to bring 100 or something, and he's going to bring, we sorted out Legos this morning, we were bringing 100 Legos, and we're trying to do 10 of each color, but we only had 9 colors, and so it was kind of disappointing, because he wanted to bring 100 Capri Suns. I was like, not bringing it. Okay, I'm going to graph x squared and x to the fourth on the same graph because I think that you can see what's happening better on this. Yeah. I told him to take 100 dominoes. Okay, that's x squared, and then that's x to the fourth. And when you just look at it like that, you might think, well, x to the fourth is just skinnier, right? Is that what you would say if I asked you the difference between x squared and x to the fourth? Yes. But what if I zoomed in here? And I know you can't do this on your paper, but if I zoomed in here at the 0, now that's x squared. Now that's x to the fourth. What does it look like on the x-axis when it's x to the fourth instead of x squared? Want me to do it again? How do I regraph this? Graph. I have a regraph button on mine. I'm going to zoom in again. Ready? Zoom in. Go. Ready? This is x squared. This is x to the fourth. Do you agree that x to the fourth looks like it kind of touches the x-axis more than x squared does? But really, they both only touch at 0. Do you agree with that statement as well? They do. They both just touch at 0. But the idea is, if you have a higher degree, that this will flatten out on the x-axis more. I should have put the flatten out picture on here, huh? So let's put the higher the degree, the more it flattens out on x-axis. We could also look at odd degrees and do this. If you think about x cubed, do you remember what the graph x cubed looks like? Nothing. X cubed. It's like an S graph, right? You don't have to draw this one, but the higher the degree, the more it flattens. Oh, look, that's not right. If we did x, oh my goodness, why do I hate this thing so much? Rachel, I'm with you. Only on this one though.
I think we should go back to John. Or just whiteboard. We should go home. Whiteboard. I like whiteboard.
That's not what I want. Alright, watch this. Let's see what this is. This is x to the third, which kind of still flattens out.
That's what it says quit. Go home. What did we say? Quit and go home.
I don't know why I try to show you guys anything. X to the third, and then look at x to the fifth. It's still an S shape, but it flattens out more too. So just know that it can happen with odd functions as well, where it flattens out still. So just know that that's what we're talking about here. So this is called multiplicity. Multiplicity is when your graph is going to kind of flatten out or sometimes we call that double roots. So if you look at the next page here, I was so excited. Multiplicity, I put an exclamation mark. And it's in all caps. That's why I put the exclamation point, because I was in all caps. So I added the exclamation for extra stuff. You get bored, you should look up this movie that was made in like 1990 called Multiplicity about this guy just like cloning himself over and over again. And each clone gets a little dumber. So. Multiplicity. If x minus r to the m is a factor of a polynomial f, then r is called the zero, which we know, and m is the multiplicity. So whatever the exponent is out there is the multiplicity, and the multiplicity tells us a lot. So if r is a zero of even multiplicity, so let's say it was like x minus 3 to the 4th power, if that's an even number, one, you know it's going to flatten out kind of like x to the 4th did, but we also know that it's just going to touch the x-axis. Touches the x-axis at that zero. It's not going to cross. So if that would be a 0 at 3, it's just going to come in and touch the x-axis, kind of flatten out like that, because we know that like x squared just touches the x-axis. The higher the degree, the more it flattens. And if your power out there is an odd number, then it will always cross the x-axis, like what we just did with x to the 3rd and x to the 5th. The bigger the number, the more it flattens out, but it would actually cross the x-axis, which means part of your homework today, you're just going to be looking at some functions, stating the multiplicity, and telling me whether it touches or crosses, which is very helpful when you're graphing these, which we're going to do tomorrow, to know this little trick. Okay? Multiplicity. Not necessarily. Like our graph could end up looking like this, like. But for every 0, I would know before I graph this, here and here would have to be like an odd degree, yes? But here I would know it would have to be something to an even number, like x minus 2 squared. The whole graph isn't a parabola, but that 0 itself is just touching there. Does that make sense? We'll get to that more when we're graphing all of these. But this just says, state the multiplicity of each 0 and state whether the 0 crosses or touches the x-axis. And again, right now they're all factored because we haven't dealt with that otherwise yet. So you should be able to tell me the zeros of this, because the zeros are just if you set each factor equal to 0, yes? So do you agree by looking at this, I could say there's a 0 at 4, there's a 0 at -1, and there's a 0 at -3, because that's just, the factor is x minus r, and the 0 is r. And it's really easy. The multiplicity is just the power. So if this one has a multiplicity of 2, because that's a 2, what does that mean? At 4, is it going to touch the x-axis or cross the x-axis? Because it's even. See how that can be helpful when you're graphing these? Yeah. There's a point to math. Hooray. There is. I don't know. Graphing calculator, but what? It says multiplicity of 2. Touch. What about x equals -1? What's the multiplicity? So is it going to touch or cross? Odd cross. What about -3? Yeah, we don't put a 1 out there, but do you agree that that's a multiplicity of 1? And when you graph a linear line, the 0 of it has a multiplicity of 1. It doesn't really flatten out, but like if you graph the line, I don't know, let's just pretend this was the line I was graphing here. If it has a multiplicity of 1, it just goes straight through it. It doesn't curve and make an S like x cubed. It doesn't just touch it like a parabola. Like it just goes straight through the graph. But it is odd, so it is still going to cross. With me on that? Multiplicity. Something else that they want you to know when you're talking about graphing is that if f is a polynomial function of degree n, then the graph will have at most n minus 1 turning points. And that's just something that it's not always true that it has that many, but it's the most that it could have. So I just wanted to show you what I mean in terms of x squared. What's the degree of x squared? And do we agree that this is going to look like this? How many turning points does that graph have? 1 is 1 less than 2. Do you agree with me with that? So if I had like a degree 7 function, what's the most turning points that it could have? 6. It's just 1 less. Again, do you have to know that? No. But if they gave you a graph, you could tell me what the highest degree it could be by looking at the number of turning points, right? Like if I gave you a graph like this, what's the... It has 3 turning points, so that could be a degree 4. Could be higher than a degree 4 because it doesn't necessarily have to have that many, but it has to be at least a degree 4 function. Okay? So that's just turning points. And the last thing, which is something, again, I know you did this in Algebra 2, if pre-calculus we did this, is knowing how the end behavior of a graph. And if your graph is odd or even, you can tell how the arrows are going to go, which is, again, useful when you're graphing because you don't have to keep picking a million points and making an XY chart. For an odd function, I always think about x cubed. For an even function, I think about x squared. Those are odd and even functions we should know. But if it's odd, I'm going to just write here x cubed for kind of an example. Your arrows are always going to go in opposite directions. I'm going to draw a picture here of an arrow, but then I'm going to write it out the way you have to write it out, and hopefully this will jog your memory from pre-calculus or Algebra 2. But think about x cubed. When you graph x cubed, it's like that S shape, and the positive side goes up, and the negative side goes down. Yes? And for x cubed, it's just that lovely little S shape. For any odd function, if the leading coefficient is positive, that's what the arrows are going to look like. And we say when x approaches infinity, so as x gets bigger, what's happening to f of x, or what's happening to y? As x gets bigger, y is going up. It also gets bigger. So we say that f of x goes to infinity. And as x goes to negative infinity, so as x is getting smaller, what's happening to f of x, or the y value? It's going down. It's going to go to negative infinity. If you think about transformations, when you throw in a negative in front of it, it's going to flip it. So if you know that this is what happens when it's odd and positive, when it's negative, it's going to switch the arrow. So now the bottom is going to, or the left side is going to go up, and the right side is going to go down. Do you have any memory of doing this in Algebra 2? Like this part's always the same. As x approaches infinity, f of x approaches something. And the little arrow is what we use for approaches. As x approaches negative infinity, f of x approaches something. Like that's this part you write every time. And then your answer just changes depending on the degree. So for negative leading coefficient, the positive side goes down, the negative side goes up. Or I always remember that odd, it's like disco. And it never gets old.
That would be like negative x to the third power.
Yes. And for even functions, you should know this already because we've done so much with quadratics, that if the leading coefficient is positive, like x squared, we know that both arrows point up. So that just means that both, as x goes to infinity and as x goes to negative infinity, the y values both point up. So I'm just going to draw 2 up arrows. But when they ask you for end behavior, you got to write it out like this. So as x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x also goes to infinity. Practice those infinity signs. I've heard that Mr. McClure teaches you to make infinity signs with 2 circles, and I don't approve of it. Write them out. Start in the middle. Loop-de-loop. Do it. Well, my pre-calculus students all make their infinities like this.
That doesn't look like an infinity.
Boo. Start in the middle.
Are you sure that's infinity?
No, that's 2 circles.
Next to each other.
Looks like an eyeball. if the leading coefficient is negative, we know that when you put a negative in front of a quadratic, it flips it over. So both arrows are going to point down. So we would say as x goes to infinity, f of x goes to negative infinity, and as x goes to negative infinity, f of x also goes to negative infinity. So if they ask you for end behavior, I expect that you write out this whole x approaches stuff. Eventually, when we're graphing, we just use the end behavior to help us. We don't actually have to write it out like that. But again, very useful thing to know, because when I'm graphing one of these, it's an easy way to check that I at least have the end arrows correctly, if it's even, that they're pointing in the right direction. So pretty much all you're doing on your homework today are answering these same types of questions, but they're like, it's like A, B, C, D, you know, your favorite type of stuff. So I thought I would do these. You'd be so happy I typed these out for you. What are we going to do when we don't have 2 hours delay and you have to write your notes again? Oh my gosh, we're going to forget what that's like. I know, we're going to actually like learn for 48 minutes. I'm so excited.
Yeah, I don't think we're gonna have 2 hours delay for the. I think we're gonna have 2 hours delay for the.
No. I thought we wouldn't have one tomorrow, but Miss Hodge says it's going to be like 4 degrees and then wind chill. We'll probably have one tomorrow.
Yep.
But I'm feeling really good for Thursday and Friday.
Nope.
I've already given up tomorrow. But
No. It's supposed to be 0 for the next.
If you think about it, we've had the easiest second semester.
so far. Well, there's some people that haven't even been back to school but like 2 days. So, all right. So this is all the stuff that we've learned today. A says list each zero and its multiplicity, and B to say whether it touches or crosses. You can pretty much do that in one step. They just wrote it out as A and B. C, determine the maximum number of turning points on the graph. That's the degree. And then D, do the end behavior. So for C and D, we actually have to think about like what would the degree be if we worked it out. But for A and B, we should be able to do that first. Yes? 0 at x equals 7 and at x equals negative 3. And the multiplicity. Multiplicity is just the power on the outside, yes? So this would have multiplicity 1. This would have multiplicity 2. Stop me if you have no clue what I'm saying. Guys, stay awake. He's in front of the class in pre-cal and he's still stuff every day. Right there in that seat. That's why he's not in pre-cal anymore.
Lucky.
B, determine whether the graph crosses or touches. What about x equals 7? Does it cross or does it touch? It's odd, so I'm going to just write that underneath there and not rewrite it all. And an even multiplicity, do you agree we can say that it touches at x equals negative 3? That's what we did before, yes? With me so far. Now for C and D, the maximum number of turning points and the end behavior, we need to know the degree and we need to know the leading coefficient. So you don't have to multiply all this out. You could, but you don't want to multiply all that out. But you should be able to look at this and think about what would be the biggest term if you multiplied it all out. If you FOILed this out, do you agree that would start with an x squared?
Yes.
And if you just took this times this times this, do you agree or disagree that that would give you your first term in that problem? And that's going to be the biggest time. You just multiply the biggest x in each one. Which means I can say, without multiplying it all out, that my leading term is 3x to the third. You see what I'm doing on that?
Yep.
If you want to multiply it all out, you can, but by no means should you be doing that. You need that to answer C and D, because now I can say, well, this is a degree 3, so what is the maximum number of times that this graph could turn? 2, and you can just say 2 there, because that's the question that it's asking. Turning points here, let's go ahead.
So why is it x cubed? That's what I want to know. It's like, it says 3x.
Because I'm multiplying. Like if you multiply this out, do you agree that would be like 3x minus 21? So you multiply the 3 to that. And then if you FOIL this out, do you agree it would be x squared plus blah blah blah?
Oh yeah, because that's x plus 3 squared, not just x.
And you'd have to multiply it out, yes. Okay, so you have to think about multiplying those out. So now for part D, if you get this part right, it's just making sure you know odds should go in opposite directions, and it's odd and positive, so positive goes with positive, negative goes with negative. But a good practice today would just write out what's going to be the same every time to practice doing this. When they ask you for end behavior, you're going to write as x goes to infinity, f of x goes to something. from there, you got a pretty good guess there, right? So it's either going to be infinity or negative infinity. And this you do have to know. When we have a test, you got to know that. An odd positive, positive stays positive, negative stays negative. Or just think of x cubed. The right side goes up, the left side goes down. And odd will always be in different directions. Disco. An odd and positive, if you match it up with the little table that we drew out. So I think I have one more on here. You start that one. Go. Yeah, same directions, A, B, C, D. And the good news is it's right above there that you can look back at it. So do this one. That's just a half. I just didn't get it written very nicely. Think about your zeros, multiplicity, top, touch, or cross, and then think about what the degree would be. That's kind of the trickier part of this. Remember doing this in pre-cal, Bryce? We just did this, chapter 2, I don't know what you're doing. Those of you that haven't had pre-cal in a while probably don't remember. Well, you've never had pre-cal, so we did this, chapter 2. That in behavior chart, I copy and pasted from my 2-3 notes from pre-cal class. Like, word for word. That's why I'm such a slacker in here with my notes, because pretty much everything I teach in here, I've taught in either Algebra 2 or pre-calculus, so I can just, like, take them all my own notes. Genius. Hold on, let me do this part. You just what? I do try to make up rules. But it doesn't always work.
I'm pretty sure it's
What if this was x squared? I would say, right? Like, look at it. But then you had to think about that little too, right? Then that would make that. So you can't just add them up now, but you have to multiply that and then do it, right? That's what, yes, that's all you're doing. I'm just saying that you can't always just say, look at the outside. I'm not telling people that, because some people will always not think about that. This will be part B, yes. You with me on A and B? You agree with me on that? What about on this one? What would the degree be on this one? Oh, yeah, well, we gotta get. Do you agree if you work this out, this would be x squared? If you work this out, this would be x to the third. And so if you multiplied, but pay attention on this one, it is definitely x to the fifth, but your leading term would be negative 2x to the fifth. So your leading coefficient is actually negative because of that negative 2, which is going to that's going to affect your end behavior. So for part C, the turning points are 1 less than the degree. So if you get the degree right, you should have no problem with turning points, but just make sure you're multiplying that out correctly. Odd should go in opposite directions, but that negative flips it around. So the positive actually points down to negative now, and the negative goes up to positive. Yes, no, maybe so. It's so warm and cozy in here now. What's wrong? Are you with me on where I got this from? How do I know what to put in here? The chart?
Yeah.
This is how I know.
Okay, I wrote down something on it.
If it's odd, do not leave here. If it's odd, it has to be opposite, and you just need to know. If it's odd and positive, positive stays positive, negative stays negative.
no homework. That's it.
So try those. No, you do have homework.
But not letting it pass something late. check. Okay, I'll just play a check.
51, 54, 59, 66, 67. 5 problems.
That's like nice.
I will tell you, there's